Directional field and numerical method. Directional field or slope field are useful for investigating first-order differential equation. In particular, we consider a first differential equation of the form y prime equal f of xy. So for example, let's create the differential equation of y prime equal x squared plus y squared minus 1. So to do this, we go ahead and pick the order pair for x, y, and we'll calculate what is y prime, and we do as many as we can. Okay, so we choose the value for x, y. So 0, 0, y prime. So when we plug 0, 0 in, we get negative 1. This means at the point 0, 0, the slope of the function is negative 1. So I'm going to make a small negative 1 slope at the point 0, 0. Okay. Let's see, at 1, 0, what would happen? 1, 0, 1 plus 0 minus 1, this equal to 0. So at 1, 0, the slope is 0. So I'm looking at a small horizontal line. So it seems like, and let's see what happened at 2, 0. 2, 0, we have 4 plus 0 minus 1, that equals 3. So now the slope is positive 3. So the slope is positive 3. So we try our best to draw the slope. Okay, so what happened at 0, negative 1? At 0, negative 1, the slope is 0. Okay, so 0, negative 1, slope is 0. So what happened at 3, 1? 3, 1, we have 9 plus 1 minus 1. The slope is 9, so the slope increased dramatically. So it's almost vertical line like this. So it seems like we have some sort of curve that's doing that. Now, do we really need to sketch do we need to really sketch this by hand? No, the answer is no. We do not need to sketch this by hand. Normally, when we have to sketch a directional field, we will use a program. And here I want to show you, this is GeoGebra. Okay. So let's put in the differential equation, x squared plus y squared minus 1. So here we can see that this is the directional field. Earlier we scattered 0, 0, we get the slope negative 1. At 1, 0, we get the slope is 0. At 2, 1, we get the slope is 3. At 3, 1, we get the slope is 9. So it's increasing. So it looks like we kind of having a curve looking thing, right? So this program is nice. It kind of gives us some solution at some initial point. So depend on where you start. Maybe this is the particular solution that you may want, that you can have. There are more than one solution. It is a whole family of solution in this kind of problem. So let's go ahead and put this directional field onto our paper. I'll just have it right here. And let's talk about that a little more. So the length of each of these small tangent line, these are each of the small tangent line. Okay. This small length that we predetermined. So we draw the slope, and we can say, okay, well, here we can see there's something happen here. The slope increasing, and increasing, then seem like it turn, and then you can have another particular solution in that direction. Okay, or you can draw a particular solution based on what else that happened here. So right here you get a -1. That's where we have the change in direction. So you can have something that look like this. For your solution curve. Okay, so those are particular solution curve, but the vector field here, the directional field tell you what kind of curve we are looking at. Yeah. A directional field or the slope field is a mathematical object used to graphically represent solution to a first order differential equation. At each point in the direction field, a line segment appears whose slope is equal to the slope of the solution to the differential equation passing to that point. So let's go ahead and create the direction field for the differential equation y prime equal x squared minus y squared, and sketch the solution curve passing to the point -1, 2. So we go ahead to GeoGebra and we will sketch that curve. So the curve that we're looking for was x squared minus y squared. Okay. So this is the curve. I will screenshot this and we'll take it back to our page. So now we have the directional view of this curve, and let's take a look at what happened. What would be the ideal curve that kind of passed into the point -1, 2? So -1, 2 is over here. Okay, so look like the slope is increasing here. In this case, the slope is increasing. Okay, it's increasing. So that is your solution curve that passes into the point -1, 2. Let's see if I want the solution curve that passes into the point, say, let's say pass into the point -1, -1. So what about the curve passes through 1, -1? So 1, -1 is here. So look what's gonna happen here. So here's 1, -1. Look like the slope is going down. Okay. So the slope here is pretty steep, right? So it's gonna go something look like that. Could be something like that is your solution curve. If you continue with this look like something we could have the curve of the slope here -1. You could also have something that look like this. Let's level out over here, and then slowly increase, and then we have a level out over here. And slowly increasing as well. So you can have many different particular solutions depend on where you want the curve to pass to. Okay. About the solution field, let's consider the directional field for this differential equation. Y prime equal x minus 3 times y squared minus 4. Let's go back to our curve. And now go ahead and maybe change the density of this. I want a little more slope line. Okay, and make the length a little longer. I go ahead and copy this over. So let's take a look at this curve. Now, if you noted that here at -2 and 2, when y equal to 2, and when y here equal to -2, at y equal 2 and y equal -2, you see that we have the slope of this line is 0. Yeah, the slope is 0. So note that at y equal 2 and y equal -2, the slope equal to 0. Would mean y prime equal to 0. Okay, so here when this happens, we call y equal to -2 our solution to the differential equation, and they call equilibrium solution. So this means y equal 2 and y equal -2 are equilibrium solution. To the differential equation. Okay, now you look at the definition. Consider the differential equation y prime equal f of xy. An equilibrium solution is any solution to the differential equation for the form y equals c, where c is a constant. So in this case, y equal 2 or -2, those are the constant. So those are the equilibrium solution. To determine the equilibrium solution to the differential equation y prime equal f of xy, we set the right hand side equal to 0, an equilibrium solution of differential equation is in any function of the form y equal k, so that f of xk equal to 0 for all values of x in the domain of f. Okay. Now let's take a look at the next thing. Say if we choose the initial solution, in between the interval of -2 to 2 in the y direction. Note that if you take a look here, note that this equation y prime equal to x minus 3 times y squared minus 4. Y squared minus 4 is greater than 0 for all y that is interval from -2 to 2, right? So let's say what's going to happen here in this graph. Note that at x value, at x equal 3, note that this line, at x equal 3, you see the slope, everything when it be before 3, all the slope is positive. When x turns 3, the slope becomes negative. So here you can see that when x is less than 0, when x is less than 3, then y prime is going to be greater than 0, right? Greater than 0. When x is greater than 3, y prime is less than 0. And note that here, when y prime less than 0, this slope line here that you can see on the other side, let's add a highlighter, see if it helps. The slope here, it got a level out and approaches y equal -2. Okay, so it approaches y equal -2. Okay, this man we call y equal -2 is a asymptotically stable. So here this definition. Y equal k is an asymptotically stable solution to the differential equation if there is an epsilon greater than 0 for that any value of c in between this interval. Solution of the initial value is approach k at x approaches infinity. So at x get greater than 3, the slope is greater than 0 and is approaching the line y equal -2. So y equal -2 is deemed to be a asymptotically stable solution. Okay. So what happened when we're looking at the value for x that is below y equal -2? Y is less than -2. So you look at y less than -2. Take a look at y greater than 2. What happened when y greater than 2? When y greater than 2, at x approaches infinity, as you can see, the slope here is approaches infinity. this meant that we have a symptotically unstable solution. Okay, so here I can say that, well, then y equal to is an unstable solution. Create a directional field for the differential equation y prime equal x plus 5 times y plus 2 times y squared minus 4y plus y. Identify any equilibrium solution. Classify each of equilibrium solution as stable, unstable, or semi-unstable. So let's go ahead and draw the directional field. And that is x plus 5, y plus 2, y squared minus 4y plus 4. Okay. So here we get the directional field. And let's go ahead and copy this to our page. Okay, there is actually a typo in this equation. It should say minus 4y plus 4. Okay. Now here you can see that at y equal 2 and y equal negative 2 is equilibrium. Okay. So let's say what happens if the initial value problem is between 0 and in between negative 2 and 2. Okay, so it means y is between negative 2 and 2. So if you notice that if y between negative 2 and 2, it approaches y equal 2. So then y prime is approached. Y prime here is approaches 0 at y equal 2 when x approaches infinity. Okay, and the same case, y prime is approaches 0 at x approaches infinity. So this meant that this implies y equal to is stable, is asymptotically stable. Okay. Well, what happened when if the initial value for y is greater than 0, excuse me, when y is greater than 2. Okay, when y is greater than 2, y prime over there approaches, this is the slope, it approaches infinity. And y is greater than 2 when x approaches infinity. Okay, so then if the initial value starting when y greater than 0, then y equal 2 is deemed unstable.